good day. I am Irma Jane Pagaura. In this video, I will be explaining and giving some examples to the following learning objectives. So first, explain the definition of a ring and a subring and produce examples. Second, prove the properties of a ring. And lastly, the third, use the properties of a ring to prove arising propositions about a ring. So, let us begin.
So now, let's proceed to the first learning objective, to explain the definition of a ring and a subring and produce some examples. So in abstract algebra, a ring is a mathematical structure that consists of a set of elements along with two binary operations, addition and multiplication. A ring is required to satisfy several properties. Number 1, closure under addition and multiplication. For any two elements, A and B in the ring, the sum A plus B and the product AB must also be in the ring. Number 2, associativity of addition and multiplication. Addition and multiplication must be associative operations. That is, for any three elements A, B, and C in the ring, A plus B plus C is equal to A plus B plus C, and AB times C is equal to A times BC. Third, existence of additive identity. There must be an element 0 in the ring such that of any element A in the ring, A plus 0 is equal A. Number 4, existence of additive inverse. For every element A in the ring, there must be an element negative A in the ring such that A plus negative A is equal to 0. Number 5, commutativity of addition or the optional. The ring can be commutative under addition, meaning that for any two elements A and B in the ring, A plus B is equal to B plus A. And lastly, number 6, distributive property. The ring must satisfy the distributive property, which states that for any three elements A, B, and C in the ring, A times B plus C is equal to AB plus AC, and A plus B times C is equal to AC plus BC. So that's the definition of the ring. Now, for the definition of the subring, it is a subset of a ring that is itself a ring with respect to the same addition and multiplication operations. In other words, a subring is a ring that contains a subset of the elements of the original ring while preserving the ring structure. A subring must satisfy the following conditions. First, the subset is closed under addition and multiplication. Second, the subset contains the additive identity of the original ring. Third, the subset contains the additive inverses of its elements. And lastly, the subset is itself a ring under the same addition and multiplication operations. Now, let's have some examples. First, the set of integers is a ring. It satisfies all the properties mentioned earlier. Addition and multiplication of integers are closed operations. They are associative and commutative. There exist additive and multiplicative identities, 0 and 1 respectively, and every integer has an additive inverse. Next example, the set of even integers 2z is a subring of the integers z. It contains all even integers including 0, and it forms a ring under the same addition and multiplication operations as z. And the last example, the set of rational numbers q is a ring. It includes all numbers that can be expressed as fractions p over q, where p and q are integers and q is non-zero. The rational numbers from a ring satisfying all the ring properties. Now, let's proceed to the second learning objective, to prove the properties of a ring. So, I will prove the closure property for addition and multiplication in a ring. So, let's assume the pair of real numbers and the positive. In closure under addition, to prove closure, we need to show that for any a, b belongs to real numbers, the sum a plus b is also in real numbers. Proof: since the pair of R and the positive is a ring, it must satisfy the closure under addition. Thus, for any a, b belongs R, the sum a plus b is defined and belongs to R. Hence, closure under addition is proven. Now, let's move on to proving the properties for multiplication. For closure under multiplication, to prove closure, we need to show that for any a and b belongs to R, the product a times b is also in R. Proof: since R and multiplication is a ring, it must satisfy closure under multiplication. Thus, for any a, b belongs R, the product a times b is defined and belongs to R. Hence, closure under multiplication is proven. Now for the last learning objective, which is to use the properties of a ring to prove arising propositions about a ring. The first proposition, the additive identity in a ring is unique. We have the proof: let 0 and 0 inverse be two additive identity elements in the ring, or the positive and the multiplication. By definition, for any a belongs to R, we have a plus 0 equals a equals 0 plus a, and a plus not 0 is equal to a is equal to not 0 plus a. Now, consider the equation 0 plus not 0 is equal to not 0 plus a 0. By additing negative not 0 to both sides, we get the 0 plus not 0 plus negative 0 plus 0 plus negative not 0 is equal to not 0 plus 0 plus negative not 0. Using associativity and existence of additive inverse, we have 0 plus not 0 plus negative not 0 is equal to not 0 plus 0 plus negative not 0. Simplifying further, we have 0 plus 0 is equal to not 0 plus not 0. By definition, by the additive identity, we have 0 is equal to not 0. Therefore, the additive identity in a ring is unique. Now, for the second proposition, we have in a ring, 0 multiplied by any element yields the additive identity 0. We have the proof that A belongs to R, be an element in the ring, R, addition and multiplication. We have 0 plus a is equal to a plus 0 is equal to a by the properties of the additive identity. Now, consider the equation O 0a is equal to 0 plus 0a. Using distributivity, we have 0a is equal to 0a plus 0a. By adding the additive inverse of 0a to both sides, we get 0a plus negative 0a is equal to 0a plus 0a plus negative 0a. Simplifying further, we have 0 is equal to 0a plus 0. By the properties of the additive identity, we can conclude that 0 is equal to 0a. Therefore, 0 multiplied by any element in a ring yields to additive identity 0.
So, that's it! I hope that you have learned something. Thanks for watching! Bye!